Welcome back to Physics 142. I'm recording this on a sunny day in Valparaiso, Indiana, and even though I'm still stuck inside on quarantine, I'm trying to smile because there's buds on the trees outside, and there's blue sky and green grass, so things are good. And we're having a chance to talk about physics, so that's great. And we've been moving into magnetism and talking about the physics of magnetic forces. And last time we were able to write down an equation for the force from a magnetic field. And specifically, we were thinking at the end of the last class period about the force from a magnetic field on a current in some wire. So in this video, I'd like to just do an example of that. So here I have a wire, and this wire is going to consist of be bent into two half circles. All right, so here is a half circle of radius r, and here we have another half circle of radius r. And the question is, how, if we put this wire in some sort of uniform magnetic field B, so here's our uniform magnetic field, so you can think of it as just being in sort of the upward direction, the positive y direction, the j hat direction here in my picture. All right, so we're going to have magnetic field B in that direction, and we're going to run some current through this wire, and the question is, how much force does that magnetic field exert on that current? So you might recall from last time that we had an equation for this, and the equation that we ended up writing down was we wrote that the force is going to be equal to the current times the length, and specifically the length, we were able to write it as just the full length L for straight wires, but now that we have a bent wire, we need to do this as an integral, so it ends up being the integral of a bunch of little pieces of length, and each little piece of length gets crossed with that magnetic field. So we have the cross product of the length and the magnetic field. So this was the formula that we had for force, and so the question is, well, how could we use this formula and apply it to this problem? Well, the first thing we need to do in approaching this problem is we have a cross product, so we need to evaluate that cross product. And evaluating cross products means drawing in some vectors. So let's think about some sort of example dl vector. So maybe I'll pick a little piece here. Maybe this is just a little dl vector, right here. And we imagine we get a bunch of little dl vectors all along here, right? Maybe here's another little dl vector, right? We got all these dl vectors all along here. And then what I want to think about is, well, what's the cross product of this dl vector with the magnetic field B at that location, right? At that location, the magnetic field is going to be straight up, right? So there's the magnetic field B there. And so if we sort of zoom in on this a little bit, all right, let's zoom in on this, then the picture would look something like this, right? We'd have a big magnetic field line, right? There's our magnetic field, and my dl vector, right, is something like this. So here's my dl vector, and there's some angle between them, right? Some angle between them. Maybe I'll call that angle phi. And what we recall is that the magnitude of this vector, right? The magnitude of this vector is the way we evaluate this cross product, right? Is, well, a cross product is going to be dl times b times the sine of the angle between them, right? That's how we're going to get the magnitudes. The magnitude is going to depend on the sine of the angle between them. So, well, what's the sine of this angle? If we think about what that might look like, right? Sine is opposite over hypotenuse, so that's going to be this part of the dl vector right here, right? This part right here would be dl sine phi, right? dl sine phi, if we took dl sine phi, that would be this vector right here, right? And here is the thing that I want to point out then that's sort of interesting is dl sine phi. Well, dl sine phi is the part that's going to be in the x direction, right? Do we all see that? That the dl sine phi is in the x direction, right? And so if I think about, well, how much have I stepped in the x direction? Well, I stepped just a little bit in the x direction, so I could just write that as dx, right? So dl sine phi, I could replace with dx because it's a little step in the x direction. And you can see that all along this, because the dl's all sort of point a little bit this way, it's always going to be just the x direction component, right? Just that the part of dl that's moving in the x direction, right? Or you could think of it as the perpendicular part to B, right? The perpendicular component to B, that for cross products, you want the part that's crossing it, right? So it's always going to be the component that's crossing B, right? That's perpendicular to B. So that's always going to be all along here. It's going to be the X component. So we can write dl sine phi as dx. All right. So that is one nice thing that we can do here. But that's only part of the cross product, right? We also need to think about the direction. So to think about the direction, remember, we need to do the right-hand rule. And so the right-hand rule says that, well, I need to point my pointer finger along the direction of DL, curl my other fingers in the direction of B, and the answer you get is the direction your thumb points, and my thumb point here is pointing here towards the camera or out of the page, right? So the direction of this cross product is out of the page, and we can see that no matter where we are along this, that's always actually going to be the case, that the direction will always be out of the page. So what we get is that this integral is every spot along it, the cross product at every spot for every little step dl, the cross product always has the k hat direction. It's always coming out of the page. All right, good. So we know it's always coming out of the page. We know we can replace dl sine theta with dx. So let's go ahead and do that. So we have this, oops, I didn't organize this very well, but so now we have the integral of b, and we're replacing dl sine theta with dx. And I still have the I out front, right? So I times the integral of b dx. But now in this problem, it's sort of useful that b is uniform across the whole picture, right? No matter where we are, we're going to have the same amount of b. So that means I can pull that out of the integral, still in the k hat direction here. So I can pull b out of the integral. So now I just have I times b times the integral of dx. And so the integral of dx, well, that's just how far I've gone in the x direction from where I started to where I finished, right? So if I look over here, I started here, and how far did I go in the x direction? Well, from here to here, that looks like that's 2r. And from here to here, that's 2 more r's, so that's 4r. So I can just write this then as I times b times that total distance I went, 4r. In the k hat direction. Often we rearrange this to put numbers out front, so we could just say this is 4I B R in the k hat direction is the force on this wire. So it depends on how much current you have, how much magnetic field, what the radius of these circles are, and it ends up being 4 times that. That's how much force you get, and that force is going to push it out of the page.